So today we're going to talk about something known as equilibrium. Okay, equilibrium is an important concept when we're discussing chemical reactions, because when we talk about chemical reactions, we often think of them as going in only one direction, what we call the forward direction. So for instance, if you have a nice campfire, you light it, it burns, and the wood turns into smoke and carbon dioxide. But we don't think of it as, smoke and carbon dioxide and soot suddenly coalescing back into a nice log in your fireplace. It doesn't work that direction because this is what's known as an irreversible reaction. But some reactions are reversible, which means that they can go in either direction. And that's what they do. So let me give you an example of this. If we take some nitrogen dioxide, it can turn into dinitrogen tetroxide. This is easy to do in the lab. But it turns out that we can actually go in what we call the reverse direction. We can actually go in the opposite direction and turn back into reactants. So forward direction, going from left to right, or reactants to products. Reverse direction, going from right to left. Okay? And at some point, these two rates, the forward reaction and the rate of the reverse reaction, are actually going to balance out. They're both happening, and we're going from reactants to products, but we're also going from products to reactants. And these two rates are equal, and therefore we've reached what's called equilibrium. I think of this as backwash, right? Like someone says, hey, can I have a sip of your glass of lemonade? And you hand them your lemonade. They take a sip, and you notice lemonade going into their mouth, but yet you notice liquid coming back out at the same rate. So when they hand you your lemonade, the liquid level hasn't changed at all, except now it has chunkies in it. Yeah, okay. So backwash, it's a lot like this, right? You're going in both directions simultaneously, but at some point we've reached equilibrium where the rates balance out. Now, there's an interesting concept, something known as Chatellier's principle. Chatellier's principle says that if you take a system that's at equilibrium, okay, it's already at equilibrium, kind of balanced out there, and you upset the system, you stress it out in some way, the system's actually going to shift in one direction or the other, the forward or reverse direction, in order to minimize or relieve that stress. Weird, right? Well, how in the world do you stress out a system? Well, good question. You can change a couple of things, and by changing these things, you're going to stress out the system. You can either change a concentration of a product or a reactant. That's going to stress out the system. You could actually change the temperature. That's going to stress things out. Or you can actually change the pressure. Changing one of these three things is going to upset the system and force it to either go in the forward or the reverse direction in order to minimize that stress. So let's take a look at some examples of this. Let's say that you have some carbon monoxide and oxygen, and this is actually going to turn into carbon dioxide. Now, if this system's at equilibrium, and I suddenly add in a whole bunch of carbon monoxide, what's going to happen? Which way is it going to shift? Well, I like to think of this in terms of landscaping, right? So your goal in landscaping is to have a nice, even lawn. But let's say that one morning you come out and suddenly you have this big pile of dirt. Some groundhogs have been, piling it up or something in your yard. What are you going to do with all of this dirt? Well, if you're like me, you're going to shift some of that dirt over here to the right-hand side to try to balance everything out, right? To smooth out your lawn again. And that's the exact same thing that's going to happen in our chemical reaction. By pumping in a whole bunch of carbon monoxide, we're adding this big mountain of carbon monoxide to this reaction. It's going to have to shift to the right-hand side to even this out. So it turns out that by adding carbon monoxide, we're actually shifting the equilibrium to the right, or shifting it in the forward direction. Now, what would happen if instead of adding in carbon monoxide, what if we added in carbon dioxide this time? Well, in this case, we now have this big mountain of carbon dioxide. Which way is it going to shift? Well, it's going to have to shift to the left, right? Towards the reverse direction to minimize this disturbance, right? Now, that's if we add in a reactant or a product. What if we remove something? What if we remove a whole bunch of carbon dioxide? Well, now, instead of having a big mountain of carbon dioxide, we now have this gaping pit where the carbon dioxide was, right? So you can imagine that the system will shift to the right in order to kind of fill in that hole. And that's exactly what the system does, is if we were to remove the carbon dioxide, the system would shift to the right, or shift towards the forward direction in order to fill in that missing gap. Alright, so that's what happens if we change a concentration. What if we change a temperature? What would that do to a system? Let's take a look at it. Let's say that you have some nitrogen and hydrogen, and this will react to form ammonia. And it turns out that this reaction is what we call an exothermic reaction. Okay? Therm like thermometer, right, meaning heat, and exo like exit. So I think of this as heat is exiting the system, or in other words, heat is being generated by this reaction. It's getting hot. So in this case, I'm actually going to write in heat as a product. Okay, so we're actually adding in some heat. We're producing heat, right, along with our ammonia every time this reaction takes place. Now, once this system has reached equilibrium, what's going to happen? Well, what if I suddenly raise the temperature? By raising the temperature, I'm putting in this big mountain of heat here, right? So what happens? How in the world can I minimize this stress? Well, if there's this big mountain of heat right here where heat is in the equation on the right-hand side, it's going to have to shift to the left in order to minimize that stress. What if I cool this reaction down? What if I reduce the temperature? Well, now I have this nice even thing. Oh, I have this big gaping hole right here where the heat was. I'm going to have to shift it to the right in order to fill that in, right? So I would say this shifts to the right, or it shifts in the forward direction. If this were an endothermic reaction, endo means into, right? So heat is going into the system, or in other words, the heat is a reactant. You can think of it that way. In that case, we'd actually put heat over here on the left-hand side, and then it would be the opposite, right? Because if we added it in, our heat would be over here, and so forth. So you get the idea. Now, do you remember what the last way to stress out a system is? Well, it had to do with pressure, right? So let's go back to our initial reaction. Let's look at this 2 nitrogen dioxide, and I'm going to specify that this is gas, and this can turn into dinitrogen tetroxide, which also happens to be a gas. Okay. Now, what if I increase the pressure? So if I increase the pressure, what's happening to this system? Well, think of it this way. You have this balloon, right, full of these two gases. It's at equilibrium. And if you increase the pressure, it's like you're squeezing on the balloon. Now what's happening to the size of the balloon? It's getting smaller, right? So there's not as much space. So I always think of this as, have you ever had to move from like a house into an apartment? You suddenly don't have nearly enough space for all your junk, right? So what do? You have a garage sale. You get rid of some of that junk. You shift to having less stuff because you have less space. So by increasing the pressure in this reaction, I need to shift to whichever side has less stuff. And by less stuff, I mean fewer moles of gas. So if I look at this reaction, I have 2 moles of gas on the left-hand side of this reaction, and I only have 1 mole of gas on the right. Because remember, if there's not a number written, it's implied that we only have 1 of these nitrogen dioxides. So the left-hand side of the reaction has 2 moles, this side has 1 mole. If I increase the pressure, I'm squeezing on that balloon, I'm squeezing down to a smaller space. I'm going to shift to the right because the right-hand side has less stuff in it, right? It only has 1 mole of gas. What would happen if I decrease the pressure? Well, this is like moving from an apartment into a house. You move into this house and you start walking through and you're like, wow, I have so much space. The first thing you think to yourself is, man, I got to get more stuff, right? So when you decrease the pressure, you're going to shift to whichever side has more space. In this case, the left-hand side has more stuff, right? So we're going to shift to the left in order to fill up our excess space by this stuff, right? So more moles of gas, more stuff, right? Fewer moles of gas, less stuff. So increasing the pressure, shift to the side that has fewer moles of gas. All right, I hope you enjoyed that. Thank you so much.